You gotta love a problem like this. This is awesome. Like, we have a chance to possibly solve this problem. Okay. A skier of mass 65 kilograms starts at point A. During the ski course, some of the gravitational turns into kinetic energy, right? From A to B, 24% of the gravitational potential. So literally you're going to go 0.24 times mgh, right? Right? And notice that the change in height here is 30 meters, right? It's 50 meters there or 20 meters there, right? So that's going to be our h. G is 9.81. There's our mass, right? Okay, so literally that's the energy available, and then just set that equal to 1/2 mv squared, and I believe I got like 11.855. Okay, so there you go. Then it says some of the gravitational potential is turned into slightly increasing the temperature, and this is something from next year. Okay, but internal energy, basically, if you think about all the atoms, a solid, in this case the skis, right, are a bunch of atoms moving. If you add up all the sum of their kinetic energies, that is the internal energy. Right? If you average the kinetic energy of each one, that's the temperature. Okay? So the temperature is proportional to the average kinetic energy. The internal energy is the sum. Literally, it's how many joules of energy that the random vibrations have. Okay? Explain that stuff, baby. All right, and then here we've got a vertical circle problem. They love these things, right? Okay, so in that diagram, the skier, as they pass, draw and label the vertical forces acting on the skier. There are two of them. One of them is the force of gravity, or call it the weight. Don't call it just gravity. And one of them is the hill pushing up. Now, one is going to be bigger than the other one. Okay. In fact, on the final, I'm going to actually have you calculate what that upward force is. Okay. Just keep in mind, we'll be able to do that. This is a vertical circle problem. Okay. So again, there's two forces. They're both vertical. One of them is the force of gravity. One of them is the hill pushing back, right? And one of them is bigger than the other. So make sure that you show that, right? Okay, so as a radius of 20 meters, right? Determine whether the skier will lose contact with the ground. Well, let's see. At B, okay, so how fast are they going at B? 12 meters per second, right? You could just use 12. You could use your answer, right? Okay. And so what you're going to do is you're going to compare the centripetal acceleration to 9.8, right? If the acceleration is bigger than 9.81, they will lose contact. If it's less than 9.81, then they won't. Think about that when you watch the Olympics, right? Sometimes they take air when they go over the top of a hill. Sometimes they don't, right? And this is it. It has to do with the radius of curvature, right? I would use v squared over r, right? So the question is, calculate what it is. This is your radius, right? The v you get from the previous problem. Yeah. Is it bigger than 9.81 or not? And then finally, on the last one, it says that they reach that point C with a speed of 8.2 meters per second, and they stop on a distance of 24 meters, right? Determine the coefficient of dynamic friction between the base of the skis and the snow, right? So what you're going to do is, I think what we're going to say is that, well, first Suvat this, right? And find the rate of deceleration, right? So you've got the initial velocity, right? You've got the final velocity because they stop. You've got the displacement, right? Find the acceleration, and the force of friction will then be ma, right? Okay, so once you find the acceleration, multiply it by the 65 kilograms, right? Okay, and then you'll get the force of friction, and then set that force of friction equal to mu times m times g. There's a way to do it without g, without the m, right? Okay, so again, solve the Suvat for the acceleration, multiply that acceleration by the mass. That's the force of friction slowing it down. Set that force equal to mu times m times g. Okay, I'll give you a clue. The coefficient of friction is bigger than 0.1, smaller than 0.2. Okay, all right, and then the final page here has to do with impulse, right? I just threw that in there at the last minute. Didn't think I would, but what the heck. Okay, so literally impulse is equal to change in momentum, and change in momentum is, in this case, mass change in velocity. So you've got the mass, you've got the change in velocity, right? And so you want to calculate that. You want to calculate that you want to calculate that change in momentum, right? Okay. And then notice that they're giving you 2 marks here, right? So the answer is one thing. Also put the right units on there. And you can just use the units you have here. And then it says, explain with reference to a change in momentum why a flexible safety net is less likely to harm a skier than a rigid barrier. Remember that what force times time is mass change in velocity, right? And so the force acting on the skier is m change in velocity over time, right? So I believe a flexible barrier will give you more time. If time gets bigger, make an argument about what happens to the force, right? The more time you have, the less force it takes to slow them down. Therefore, the less likely it is to hurt them, okay? Yeah? Yeah. I love this problem. I think this one's on the final.